Is Kasiski examination. So it is a method used to break classical ciphers, particularly the beginner cipher. So it works by identifying the repeated sequences of characters in the ciphertext and then calculating the distance between these repetitions and finding the common factors among this distance. So it basically, let's just say if we have a common bigrams or trigrams in the plain text, so now it calculates from time to time if there are any two occurrences of any of those repetitions, they will be separated by exactly may be separated by exact multiple of the key length. This means they are encrypted in the same way. This is how it basically works. So let's just go through the code once. So in this function takes ciphertext and optionally minimum sequence length. It finds in this it finds a repeated sequence of characters and determines the common factors among these distances. The function this function returns a dictionary containing potential key lengths based on distances between repeated sequences. And then now this is the common factors and distances. This function calculates common factors between two integers. And now this calculates the common factors between two integers a and b. And now for the get factors, it computes the factors of an integer n. So now if we just take the example and run the code. So yeah, if we run the code, this is the example, and now we got the output as ABC24. Basically, ABC is the sequence that is being repeated at second instance after 4 instance. Basically, if we check this, ABC is being repeated after two characters, and then again ABC is repeated, and then again after fourth it is repeated. So basically, just like that, we are getting the output as ABC, BCD, and all the characters that are being repeated like this.
The next comes a modulus tag. Let me open the file. Yeah, here comes the code of it. So basically, let me explain you about it. A common modulus attack targets public key crypto systems like RSA where multiple keys share the same modulus n. If two users have different encryption exponents but share the same modulus, an attacker could intercept and decrypt messages intended for the other user. By exploiting this shared modulus, the attacker employs the Chinese remainder theorem to effectively compute the plaintext without factoring the modulus. To prevent such attacks, it's crucial to ensure unique moduli for each user and employ strong encryption techniques. So here comes the code shown at the screen. The code implements a common modulus attack, a method to decrypt RSA encrypted message when the same modulus is used with different public exponent. It computes the greatest common divisor GCD and the two integers s and t. Like we have used GCD, we have defined it, and s and t is being defined in the code. We have used it. We have used Euclid algorithm from on s and t. Then it adjusted the ciphertext based on the signs of s and t, decrypts each ciphertext using the respective exponents, and combines the plain text to obtain the decrypted message. So here is the whole algo. Here was a plain text, and then we will see how it's been decrypted. Finally, it demonstrates the attack by decrypting two ciphers using their respective exponents and modulus. Now let us run this code. Run without debugging it. So yeah, we got the favorable output. Now next comes the Pollard algorithm. Let me open the code in front of you. So that's the code of it, which was originally designed for integer factorization, can be purposefully proposed for primality testing. Thus, by implementing to find a non-trivial factor, it determines whether a given number is likely prime. The process involves selecting a random starting point x and a random function fx, generating pseudo-random numbers. Iteratively applying fx to x forms a sequential, eventually cycling due to the finite residues modulus and the number under test. The fluid cycle finding algorithm detects this repetition. Once identified, the algorithm computes the greatest common divisor. Like in the previous, we have only got to know what was the GCD and how we were using it with SNT for common modulus. Here also we are using the same concept of it. GCD of the differences between the consecutive elements and n. If the GCD is greater than 1 and not equal to n, then the n is composite, otherwise n is likely to be prime. If no factor is found after a certain number of iterations, the algorithm can be rerun with different random choices. While probabilistically, Pollard-Rao algorithm is relatively efficient and adaptive to primarily testing with high probability of correctness. But in some cases, it's not being preferred, like deterministic algorithms such as AKS primarily testing or Miller-Rabin testings are generally preferred. So we have the code of it here. We are using a sequential number to find non-trivial numbers of the output. It includes the function to check if a number is prime. We have function factorize that utilizes Pollard-Rao to factorize a given number into its prime number, while its prime checks here is the is prime, which checks whether we are getting a prime number or not. Here are the conditions for it. In the example usage here, the code attempts to factorize a large number, printing its prime factors if successful, or a failure message if the algorithm cannot factorize the number. So let me run this code in front of you. So we were given this, and that's the output of it. It has factorized it, it has found the prime numbers in it. So yeah, that's the explanation of our project. Thank you.